A little earlier, I think the third year in a row we've had a presentation from Jim on IPv6. Jim has been doing networking for a long time. Yeah, I mean probably before IPv4, and now has updated us on the move, or whatever it is, crawl to IPv6. You know, the impending move to it, and I don't know, I didn't read recently what exactly you're going to talk about tonight, Jim, but going to get a full update on where IPv6 is and what it means to us.
How to use it.
How to use it. What are you with now, Jim?
I'm with a large telecom company.
Okay.
I do not speak for the umpire though, so I will not.
Okay. Light?
I'm not sure.
Do you know how to do it?
No?
If you flip the little door down, bottom half.
Isn't that slide?
Yeah. Okay, flip it up. And then I don't know what you do.
It's high-tech stuff. That's good?
That's pretty good. How's the cameras?
Yeah, it's pretty much, yeah, better than it was because it was kind of washed out, so.
Okay.
Good.
All right, you ready?
I'm ready. All right. So this year I have a timer, so try and keep it a little tighter. So my name is Jim Small, and I've been working full-time in the industry since '95. So actually I don't predate IPv4, but I do go back to all the way when really IP wasn't even a major protocol yet. So been around for a while. So I have I've been working in IT for about 21 years, and the last, I think, 13 or 14 years I've been in consulting and infrastructure. So I deal mostly with networking and security, a little bit of systems and scripting, stuff like that. I've been dealing with IPv6 for the last 5 or 6 years, and about half of that, it's all I did, was just IPv6. So it's been kind of interesting to watch. I kind of got interested in 2008. So in 2008 I went to a presentation, and in 2008 IPv6 was, at least in my opinion, kind of a novelty. And I remember went to a Cisco conference back when it was called Networkers, and everybody had their laptop, and the presenter walks in, and he basically proceeded to hijack everybody's laptop, because by default, if you have IPv6 enabled, which on Vista and later, and I think OS 10.3 and later, it's on by default, and it's preferred by default. So if you don't have it locked down, somebody can basically just hijack your session. So that kind of got my attention. I thought that was pretty cool, and you know, and then it went from there. So if we look at IPv6, it definitely has been slow going. So IPv6 actually this year turned 20 years old, so it's been out for quite a while. The uptick has not been that fast. We'll kind of talk about why that is, what's going on. And I tried to spend some time thinking about just this opening slide and kind of trying to set the tone. If we look at IPv4, IPv4 has really turned into a walled garden. So for a long time people were afraid of what's called CGN, and we'll talk about that. And really CGN is just the norm nowadays. So if you look at most of the carriers or most of the internet service providers, CGN is standard. And CGN, I mean, it is what it is, but it does end up kind of turning into a walled garden, because it causes a lot of problems if you want to have direct communication, so especially for things like voice and video. And it also makes it really hard to do novel things. So, you know, walled gardens can be really beautiful, right? But it kind of tends to restrict you to what you know and what you're comfortable with. Whereas if we look at IPv6, it's a little bit of the kind of the unexplored, the future. And so there's a lot of cool things, but it's also, it's kind of the unknown. So I think part of the issue is, you know, it's new, it's uncomfortable. I mean, people have done IP for 20 years, and it is a big change. Yeah.
CGN stands for?
CGN stands for Carrier Grade NAT. So I will get into that, and it's a Carrier Grade NAT basically means I have multiple cascading layers of NAT, and it's an address conservation technique. So it's a good question, and I promise, like with all the terminology, I'll go through that. All right. So there's two things I want to talk about. I think this is roughly split down the middle. So the first is kind of where are we at in the industry, right? So I know it kind of runs the gamut. There's some companies that have already fully deployed IPv6 and they're done, right? That's a pretty small minority, but there are some, even in the area, you know, especially if you look in Ann Arbor. Most companies though haven't. Some are dabbling. So I don't make any assumptions, and I try and kind of look at, you know, when is it interesting for you? And I guess at the end of this talk, I hope I'll at least give you enough so you can decide, you know, yeah, this is interesting for me, or it's not interesting yet. Because really, I mean, you have to decide yourself. I mean, it's going to be different for everybody. And the second thing is, actually I checked, this is actually the 4th year I've done this. So if you go back and look at the MUG website, there's a lot of history. And with IPv6, I mean, if you think about networking, right? If you think about what networking touches, I mean, it touches everything. So, you know, in an hour and a half talk, you know, you can only do so much. So I do kind of dive into some areas, like I spent some time on the socket API, which I think is kind of interesting, but I can't talk about everything. So a lot of the stuff with the basics, with commands, with troubleshooting, if you go back and look at the, you know, past 3 Januaries, the slides are there, and I would encourage you to look there if you're curious for more details.
You know what, if I could interrupt just for a second.
Sure.
One thing we forgot to mention during the opening stuff. We have refreshments over here. If you guys want a cookie and a pop, the idea is you put $1 in the jar, and you can take a cookie and a pop, or 2 cookies. And feel free to get up. If you can do it quietly, get up anytime during the presentation. Thank you. Sorry.
No problem.
That was important.
That's important. Cookies are serious. Okay. So let me start with. Like I said, I try not to assume anything. You know, there's a lot of background, but let me try and cover some of the basics. So in terms of how does IP addressing work, right? So somebody has to be in charge of it. So the organization in charge of really internet governance is called ICANN, or the Internet Corporation for Assigned Names and Numbers. And they basically do internet governance, including things like DNS and addressing. And they have an arm under them called IANA, which is the Internet Assigned Numbers Authority, and they basically deal with addressing. So they deal with all of IPv4 and IPv6. And IANA will basically delegate blocks of addresses to the regional internet registries. So if we look at the world is carved into 5 regions. Each region has a representative RAR that's in charge of address space for that area. So for us, that's ARIN. ARIN does the US, Canada, and a little bit of the Caribbean. And those registries, if I need an address block, that's where I apply. Right, an end user, an ISP wouldn't go to IANA, they would go to their appropriate registry. Now, from a registry's point of view, there are 2 types of users. You can either be an LIR, which is essentially an internet service provider, or you can be an end user. Now, for IPv4, that didn't matter, and I don't want to get too much into the weeds, but for IPv6, it's important, and actually the addresses are different depending on which type you are. So an ISP or an LIR basically means when I get an address block, most of those addresses I'm not going to use for myself. I'm going to delegate them to customers, right? So I'm going to use those addresses and I'm going to delegate them to other companies, other people, other users. Whereas an end user, if I get my address block, I'm just going to use it for myself. I'm not going to give it to partners or other people. And you get a different block depending on which one you do. Now, why that matters, and especially for IPv6, is with IPv4, if you've been in the industry since the early to mid 90s, before NAT became really popular, people used to actually use public, and there's actually still a few companies that do use public addresses for everything. as opposed to just their internet presence. Since we don't have enough addresses in IPv4, in the last 10 years, it's kind of gotten to the point where everybody uses private addressing internally and public addressing just on the edge. But one of the ideas with IPv6 is to kind of get back to, I have public addressing for everything. And there are some reasons for that. Basically, the biggest reason is it makes communication a lot easier, right? So imagine when I'm calling somebody, if I have to call you and you're behind a PBX, I mean, it's not hard. I just call the PBX, I hit in your extension, and then I talk to you. But it's still, if I want to, it's still a little bit of work, right? It's an extra step. It's nice if I can just call you direct, right? So most people you'll find that have phones, they'd rather have their own phone number than have an extension. And that's the idea with IPv6. Rather than having to go through a gateway, I can just talk to you natively. Now the challenge with that is, if I get my address block from my ISP, then if I change ISPs, I have to renumber. Now if I just have to renumber my internet presence, that may not be too bad. But if I have 10,000 nodes and I have to readdress all of them, that's a pain, right? So that's why with IPv6, end user addressing gets more interesting. Okay, now with IPv4, if we look at an IPv4 address, we have 4 octets, right? So 10.1.2.220, for example. And each one of those octets is 8 bits. And the reason I mention that is when you look at people like ICANN and the registries and anybody who deals with addressing, they're going to talk in what's called CIDR notation. So that's what this /8 is. So a /8 means we're talking about the first 8 bits or the first octet. So if I look at IPv4, each number can be 0 to 255 or 256 possibilities. So that means with IPv4, I have a theoretical possibility of 256 of those /8s, right? Which is roughly 4.3 billion addresses. So that's my total. Now out of that, I can only use about 221 of those. And that's because if you think about it, right, I can't use 0, I can't use 127, I can't use private addressing including 10, I can't use multicast, and my traditional class E block, which is 240 to 255, none of those I can use, right? So if I take all that out and a few more, I'm left with 220.8 usable blocks, which is about 3.7 billion. So it sounds like a lot. However, if we look at, remember, so IANA delegates blocks to the RIRs then turn around and delegate them to end users or ISPs. If I look at all 5 RIRs, I have 3.64/8s left, which is about 60 million addresses, which is a problem. It's not enough. So that means that I've allocated a little over 217 of those blocks have been basically given out to people, to companies, to organizations. And out of those, 168 are advertised. So advertised means if I look in BGP on the internet, so BGP is the routing protocol that I use to route traffic on the internet. If I look, I will see 168 of those blocks advertised. So not all of them, but most of them. So just to give you some background. Now, one thing, when I did this talk last year, I think I kind of got the impression for a lot of people, when we talk about IPv6 and we talk about, the internet's oversubscribed and there's too many people and we have IoT and blah, 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 I think it's what a lot of people hear. They're like, come on, there's plenty of addresses, it's not a problem, you're making it up, right? So-and-so gave back their /8, we'd be fine. So I wanted to take just a little bit to give you some background about why is IPv4 a problem? Why have we gone through all these addresses? So if we look at the population, we're a little over 7 billion. And out of those 7 billion people, 43 or 44% of them are online. So if everybody on the world is online at the same time, which obviously this doesn't happen, but if it did, you can see we already have a problem, right? Because that's just users. That's not counting servers and infrastructures and routers and firewalls and all the other stuff we need to make the internet work. Right? So if you start kind of thinking about how many people are using the internet, you can see it's getting pretty crowded. In addition, we also have the mobile space, right? So now with the mobile numbers, it depends on where you look. So I looked at the GSM Association, and they basically said if you look at all 3G connections, there are right now about 7.6 billion. Now, not all of those are IP-based yet, but it's going that way really fast. Pretty much, I can tell you from working at one of the largest carriers in the world, everything is going IP. Everything else is going away, right? If you look, the goal with all the major carriers in the US is to totally eliminate POTS, like your legacy phone lines, by 2020. Like, it's gone. And Europe has the same goal. No more analog, everything is IP-based. So this is where the world is going. So again, that's a challenge too, right? So if we have 7.6 billion already, how do we make that work in an addressing system only designed for 4 billion? Then we also have what's called the Internet of Things, and you might have seen this M2M. So M to M is machine to machine, right? So for example, let's say I have a vending machine, and I want that vending machine to tell me if it's out of Coke. Well, I can put a sensor in it, and I can say, hey, if you sense that the Coke's out, shoot a message to the data center, and so I can dispatch somebody to fill it back up. So there's a lot of things like this going on. That's the M to M, or the IoT, Internet of Things category. And there's more and more of these things cropping up. So right now there's about 5 billion of those sensor type devices online. And the most conservative estimate is from Gartner. They said that's going to be 25 billion in the next 5 years. Some people think 50, 100, or even 200 billion, which may sound kind of fantastic, but we'll come back to that in a minute. But again, so you have all of these things trying to get online. So that's what's creating a bit of a challenge. Now, in terms of, I think when most people think of networking, we still tend to think of this guy, right? When I talk about a network, I think about my laptop, maybe I think about my smartphone, but I kind of think of things that I'm holding, right? But I believe last year, the number of M2M devices, or devices basically that don't interact with people, they only interact with other machines, the number of those devices passed the number of human use devices. And it's going to grow by orders of magnitude over the next 5-10 years. In fact, Stanford, I didn't show it in here because I think it's almost too mind-blowing, but Stanford thinks that in the next 10 years, we're going to have over 1 trillion of these things online. So not everybody agrees with that, but I mean, the number is going to be massive. So if we look at, this is microcontrollers, right? So this is an integrated circuit analyst firm, and they look at microcontroller shipments. Now, not all microcontrollers are networked. So if I have a sensor and actuator, right? So let's say I'm building an autonomous vehicle. I have to have sensors on the car, and I have to have actuators to make things happen, right? Or anything. So all these sensors and actuators are usually run by a microcontroller. And these microcontroller assemblies, we sell billions of them every year, but they're not all networked yet. So what's changing is, in the next 5 years, the cost for me to include networking componentry on this integrated circuit, cost is going way down. And Gartner says that by 2020, it's going to be less than $1 a unit. So it'll be so cheap to give you network connectivity for cellular or Ethernet or wireless or whatever, that it'll just be a given. Because it's going to be so cheap, it'll be on everything. So not necessarily everything will have the network on, but it'll have the capability. And if we look at this category, we have tens of billions of new devices every year. So by 2020, if all of these devices are going online, and this kind of shows the net new, that's where people are getting that 200 billion number, right? So if we keep throwing all this stuff online, this is what's causing this strain with IPv4. Now, I don't want to go through this too much because of time, but just to give you a quick idea, I mean, this is how this is being used today. And I can actually tell you right now, I am working with a utility, and basically all of their stuff is all online, right? And one of their concerns is security. But everything's online. I mean, the days of analog gauges and like having people watch something, those days are long gone, right? Everything's automated. So if I'm dealing with, power, if I'm dealing with water, wastewater, gas lines, fleets of trucks or cars, all of those things have sensors. They report back to a central monitoring station, and everything's automated, right? And we only want to get a person involved if something interesting happens, right? If something bad happens, if there's a problem, we need a person. But we don't want somebody, just kind of staring at a bunch of gauges that are good. So all of these industries are exploiting this to basically automate more and more services. Now, going back to that 3.64 number I showed you, this is how we get that. So like I said, IANA is totally out of IPv4 addresses. And if we look at the registries, so APNIC serves Asia Pacific, RIPE serves Europe and the Middle East, and LACNIC serves Latin America. Now, these three RIRs are what's called depleted. So depleted means they're not completely out, but they're in a rationing mode. So APNIC, what happens is they were burning through addresses really fast, and once they got down to 1/8, they said, okay, everybody in our region now only gets 1,000 addresses one time for the rest of eternity, and that's it. Because they have to do that, otherwise all the addresses would be gone. So that's how they survive and they don't completely run out. So that's why you'll see that these guys are going really slow, because they're rationing their addresses to try and prevent complete run out. ARIN is our registry, and they decided we're not going to have any reserve. So in September they just totally ran out, and they're at 0. And AFRINIC is the only registry that has any addresses left. They enter rationing mode when they get down to 1/8, which should be mid next year. So that's it. Now, one common thing that I still see a lot of is I still see a lot of people, or hear a lot of people that'll say, so-and-so company has a /8, or so-and-so university has a /8, and if that university would give that /8 back, we would need IPv6 and we'd be fine, right? And you know, I mean, I can see that, because a /8, I mean, that's almost 17 million addresses. I mean, that sounds like a lot, right? So the question is, how long, if somebody gave a few /8s back, how long would it last? So you can actually go to podaru.net. That site is run by Jeff Houston. He's the chief scientist for APNIC Labs, and he publishes all the data. So if you're interested in internet data, I mean, that's a treasure trove. And here, he's published up to 2011, so 2011 is when IANA ran out, and then the numbers are skewed because there's not enough supply. But you can see that in 2011, when we ran out of addresses in February, we still went through 1/8 a month, right? Now this is 5 years ago. The internet's been steadily growing since. In fact, with IoT, it's accelerating. So 5 years ago, we'd go through 1/8 a month. So even if we got like 5/8s back, I mean, really, it'd give us another 3 months. Right? So it's important when you're looking at, you know, what you're going to do or how things are going to work. You want to look at what are the numbers and how fast do things last, or how long do things last? How fast do we burn through things? Because 1/8, I mean, you're talking, you know, 2 or 3 weeks, really. You know, it wouldn't matter, right? So keep that in mind when you're formulating your policy. Now, I also took this data and I built a chart to try and give some context. So this red line on the bottom here, this is the address supply. So in terms of growth, the average growth on the internet, not counting for IoT, so we're going to conveniently ignore that, right? Even though it's the biggest category, growth has been about 6% a year. So if we say, okay, you know, let's ignore IoT, and we're just going to say that 6% growth continues, that's what this is here. This would be the demand for addresses, right? So between 200 and 300 million net new addresses per year that IANA would need to supply. Of course, it doesn't have any. This red line is what's actually left, right? So you can see, and basically the curve slows down just because there's not enough supply. You know, so only part of the world can meet the supply. And essentially, I mean, this is where we're at. I mean, we're pretty much about out. So this line basically is the deficit. So if we say, how many addresses do we really need versus what we have, this is the growing deficit, right? And you can basically see that it's starting to get significant. That's what's driving CGN or carrier grade net, because ISPs have to do it, right? I mean, if I'm oversubscribed like 4 or 5 to 1, I have to deploy lots of net to survive. That's what's going on right now. Now, one thing that hasn't gotten a lot of press yet, but I'm sure it will, is this unadvertised space. So if you remember, question.
Yeah, real quick, how much of that growth would you attribute to like panic ordering of IPs and people hoarding and stuff?
That's a great question. So I don't think very much, because so the way internet governance would really be a whole talk, but just to try and give you a brief answer, the way allocation works is if I go and apply for an address to one of the registries, I have to show need. So I can't just go to ARIN and say, you know, I want a /8. They're gonna be like, okay, well, in order to get a /8, you have to do A, B, C, D, and E, and you have to provide documentation. You have to have a legally incorporated company, you have to show some kind of a business plan, you have to prove that you're actually gonna use the addresses. So there's actually a lot of background check. You can't just go and get it. So, you know, now you can game any system, so, you know, maybe a little, but not much. I mean, the way the system is set up, it's not really an open market. You have to show a need to get it. So I don't think there's too much of that. Now, going back to what I said about IANA, not all of the space is advertised. So we do have some organizations that basically got IP address space and they might be using it internally. Like I can think of a few companies that use public address space internally, but they don't advertise that space on the internet, right? So especially companies that have been around, you know, for 30 plus years. Now, we're going to talk a little bit about the addressing market. If you listen to people that want to sell addresses, they're going to say, oh, we have 1 billion addresses left and there's no IP address crisis and everything is fine. So what they're talking about is, they're talking about this unadvertised space, right? So of course, you know, somebody that's trying to sell you something is always going to be a little marketing, right? So 1 billion is kind of like rounding up a little. Actually, there's about 850 million addresses that aren't advertised. Now, it's not that they're not used, right? It's kind of like if I buy a third car and I store that car in the garage, or you know, maybe I just drive it at a closed racetrack or something. It's not like I don't own the car. I might not drive it on the public roads, but I might still use it. So these addresses, they're typically used, but they're not advertised to the internet. Now, what that means is, if they're not advertised to the internet, maybe they'd be willing to sell them. And so the people in the addressing markets, they're basically saying that if you give these people enough money, they're going to sell you the address space. Now that's not really true. Some of these people, like the DoD, for example, no matter how much money you offer them, I don't think they're going to be interested, because you know, they're so big. I mean, even if you offer them $1 billion, I mean, to them that's like a rounding error. It's a little bit like, go away. So I guess the question is, and really nobody knows the answer, how many of these people would be willing to sell their address space? Because I work with a lot of these companies, and some of them really, they don't want to. They're not interested. And if I'm a $100 billion company, even if you offer me like $200 million for my address space, you know, I might think about it, but if I have to go renumber all my critical stuff all over the world, question?
Minor point. But I thought that it was not permittable under ARIN policy to sell or otherwise market address space. That if an entity were to try to divest themselves of their address space, they'd have to return to ARIN for allotment.
That's a great question, and I would love to answer to that. I'd be happy to talk about that later, but it's kind of that is true. But there's always a way around things. So ARIN, in the end, ARIN has to approve it. But you can pay somebody for the rights, right? So there can be conditions, but there's, you know, like I said, there's always a way around. So this is kind of the question mark, is how many people are willing to sell that address space? Now there have been a lot of sales this year, a lot of transfers, and what I'm assuming is that's going to grow, you know, based on what I saw this year, about 3/8 were basically sold and put on the internet. So assuming that grows about 18% a year, that's what the curve looks like. This shows up to 2020. I'm actually curious to see, because you know, you could probably make IPv4 work forever or for a really long time, but how many layers of NAT are we willing to put up with? You know, 4, 5, 6, right? Because I mean, if you get up to 1 trillion devices, it starts getting really hard. So I mean, eventually it'll get to the point where some people will be like, God, you know, like, you know, even IPv6 is better than this. When does that happen? Does it happen in 1 year, 2 years, 3 years? That's a tough question to answer. So this is kind of, you can kind of see that in the next 5 years, it's really going to get tough. Because at the end of the day, you still need some public addresses, right? You can't do everything with NAT and privately. So that'll be interesting to see how far it can get stretched. Okay, I did, I gotta watch here on time. I did want to talk a little bit about NAT, and kind of explain what CGN is. So traditionally with NAT, what most people think of with NAT is kind of like with a home network, right? So I have like a Linksys or a D-Link or some kind of wireless router at home. Basically that has a public or routable address on the outside interface, and on the inside interface it has a private network, like maybe 192.168.1. something. Right, so when I'm on my laptop or tablet or phone or whatever, I basically go through that router, the router does NAT, and everybody sees me as that one address, right? That's your traditional NAT. So that has worked pretty well up until maybe 3 or 4 years ago. Now the internet's oversubscribed by about 4 or 5 to 1, so that's not enough. So now we have what's called carrier grade NAT. So all carrier grade NAT is it means we have cascading layers of NAT. So we have maybe, instead of one NAT device, now we have 2 or 3. So for example, if I'm an ISP and I'm trying to conserve my public IPv4 address space, now I'm going to give you what's called a shared address. So some ISPs will actually use the private address space. Like some ISPs have actually forced their customers to renumber because they're saying, we're going to use 10 on the outside so you can't use it in your internal network. Which is kind of a pain. So ARIN actually set aside 100.64/10 as a special shared address block for ISPs to use for CGN. So you might see a little of this. So basically, but this is not routable because this is not a unique address. So I will get, instead of getting a public address, I'll get like a semi-private address on my outside interface. And then basically this gets routed somewhere into my ISP's network, into some massive router, and this router is then going to translate into a public address. So that way, instead of my ISP having to give me a public address, maybe it uses one public address for my entire neighborhood, right? And we all sit behind kind of like that giant NAT router. So the nice thing about that is that it lets the ISP preserve IPv4. And in a sense, it's positive because it sure beats a broken internet, right? At least the internet continues to function. So that part is good. The bad part about it, there's a few problems. I'll talk about the problems, well actually, so there's a few problems, and actually there's more than a few, but just kind of high level. So probably one of the biggest problems is security, right? So most people, most sites, if you have somebody that's doing bad things, you're going to blacklist them. You'll say, oh, so-and-so from this IP is causing me problems, I'm going to blacklist that IP. Except now the problem is you just blacklisted a neighborhood or a region because that's no longer one user. So security becomes more challenging. The other thing is communication. So communication, like gaming is the big one. Most people who do CGN, like if you do a lot of gaming and you call up your ISP, they'll take you off of CGN because it just doesn't work well. However, and people say, yeah, but gaming, that's for kids, it's not for me, whatever. But it does affect us because anything with voice or video is a problem, right? And SIP is pretty popular. Like, I don't know how many people use Vonage or something like that. That's SIP. So if I'm doing point-to-point voice or video with somebody else, that's communication. That's hard behind CGN. So usually if I'm doing that behind CGN, now I need a third-party service. So if I just had NAT, I would just need a stun server, and the stun server would help me figure out what the remote IP is. But with CGN, that usually isn't enough, and I also need what's called a turn relay. So basically it means that with CGN, I can't directly talk to somebody else anymore. Now I have to go through a relay. So this is where some of the hidden costs of CGN come in, because if I'm the person that's supporting like that voice or video service, now I have to have relays on the internet, and all of that traffic has to relay through me, which means I have to incur a lot of bandwidth expenses. So I do hear a lot that people will say, who cares, just put more layers of NAT, it doesn't cost me anything. Well, it depends. If you just run a simple website, probably won't cost you anything, right? As long as you don't do things like embed addressing in your authentication. But if you run any kind of a communication service, that's not true, right? That there is a cost. It's kind of incremental, it's subtle, but these are the kinds of things that CGN introduces. Okay, so we talked about CGN as a preservation strategy, but if I keep growing, at some point I need more addresses. So how do I get the addresses? The way I get the addresses is the market. So I can go to the market. This is one broker. I mean, there's tons of them, and essentially the going rate for an IPv4 address is somewhere between $8 and $11 an address. So for some, especially for smaller companies, if I have a Class A address, it's worth 150 million. That's some money. So a lot of people are selling and trading addresses. Now, it's still, at the end of the day, it still has to get approved by the regional internet registry. But there's a lot of people who really need addresses badly. So there's a lot of activity going on here. Again, I don't want to get too much into the weeds, but one thing you'll notice if you look at this is the smallest address is a /24, which is 256 addresses. You'll notice that there are no smaller transactions, and that's because on the internet, right now, that's the smallest block you can route. And it'll be interesting as we try and stretch IPv4 further and further to see if the ISPs will be willing to accept more. Because there are problems. There's so many details, but I don't want to go down that rabbit hole. But there are a lot of, and even with buying an address, there's a lot of stuff you have to watch for. Is the block clean? Is somebody else trying to advertise it? Was it used for malicious activity, so it's on blacklist? So I mean, this is not trivial. You need to spend some time thinking, but it is an option. Okay, so that was the IPv4 story. So I want to talk a little about IPv6. Now, before I start talking about where we're at with adoption, one thing I wanted to point out is I don't hear it much anymore, but every once in a while I'll still hear somebody say, IPv6, it's too hard, it's too different. Can't we have like an IPv4.1 or something where maybe we just add a 5th octet instead of, quadrupling the address size? And at first that might sound kind of good, but I want to talk about this for a minute because it's important to think about if I have a new global communication standard, how long would it take to develop and adopt that? And basically, if I start thinking through that, even if I added a 5th octet to IPv4, right, to try and stretch it out, that means that, first of all, I'd have to go to all the operating system manufacturers, right? So Google, Apple, Microsoft, all the Linux distros, all the Unix manufacturers, all the real-time OSs. I'd have to get all those guys to agree that my specification makes sense and they're going to have their developers implement it. And the first thing that any one of those guys would say is they'd be like, show me your approved RFC from the IETF. And you'd be like, okay, fine. So I'm going to go through the IETF. Okay, so I'm going to propose my standard, the IETF, if I'm lucky, 5 years later, I'm going to have an approved standard, if I'm lucky, okay? Now, then I have to go back to those OS guys and say, please, 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 please implement this. And they're going to say, well, show me that there's a market driver, show me that people are going to adopt it, and then I'm going to have to go to the ISPs, and you get the idea, right? Generally speaking, we can kind of look. To come up with a new standard and get it deployed is typically close to 15 to 20 years. By the time you go through the standards bodies, you convince everybody to write the code, you actually get the code rolled out into production, get people using it. I mean, if you start thinking about the whole world, right, to adopt it, it's not a trivial process because there's a lot of other great ideas. So people are going to say, there's 100 people that have great ideas, why should I listen to yours? So it's not so easy. So I don't hear this anymore, but if somebody says to you, don't worry about IPv6, there's going to be something else. There are some other things, like there's something called NDN, which is pretty sweet, but I mean, no matter how awesome it is, it's at least 10 years out. And I don't think the internet can survive for that long on IPv4. So keep that in mind. Now, that said, so the only realistic plan we have to get away from IPv4 and move to something else is IPv6. And kind of looking at it, what I want to spend a little bit of time on is, where is IPv6 at? And really, the more important question is, when is it interesting for you? Right? And I'm hoping I can give you enough of a definition of interesting that you can formulate the answer for yourself. So this is usually what most people show. In fact, there's a lot of press that, IPv6 is over 10%. But this is actually not a good source because this is Google's view of the world. And that's not a bad view, but for example, if I go to China, is Google a major player in China? No. right? China's one of the largest internet markets in the world. So, you know, this is an interesting data point, but it's not really a good data point if I'm looking at global traffic, right? So, in the US, Google is, you know, still one of the top players, although Facebook is bigger. So the other thing too, I think a lot of people see this and they think it represents everywhere. But this is just Google's view of the world. If we look at the US, in the US, Google sees about 24% of their traffic come over, or 24% of the users that visit Google are IPv6 capable, right? And actually Facebook's percentage is higher. Facebook's percentage is probably closer to 30%.
Capable or actually using it?
That's a good question, capable.
Yeah, that doesn't.
So I will, that's an excellent question, I will come back to that. Because that's an excellent,
The first time you came here to talk about it was January of 2013, and we were at 1%.
yeah, it's,
You know, now we're at
Yeah.
10%. That's
so it's you know, it's definitely,
happening.
it's definitely at the point where it's interesting. Is it interesting enough to take action? I mean, it depends on where you're at.
Yeah.
Okay, now, there are 3 major public sources of IPv6 data. There's Google, there's Apnic Labs, and there's Akamai, right? So we talked about Google, everybody knows who Google is. You might not know who Apnic Labs is. So Apnic is one of the regional internet registries, right, for Asia Pacific. And Apnic Labs is under Apnic, and the guy who runs that is named Jeff Houston. And Jeff Houston, if you get into anything with internet data, he is the man. I mean, everybody, I mean, Gartner, Google, I mean, anybody in technology, if you ask them anything about internet statistics, they're gonna talk about Jeff Houston. I mean, everybody treats, this guy's awesome. He is like the statistician for the internet. So, I like his data the best, and the great thing too is, I encourage you to be skeptical. In fact, I got questioned last year, I don't believe this. Even like when I talked to Gartner, Gartner said, that's not end-to-end. So this paper right here, and I'll share this with Jim so you can click on the link, Google published a paper explaining how do we measure traffic, right? And the way they do it is, your browser downloads JavaScript, the JavaScript tries to connect to a 1x1 IPv4 pixel, 1x1 IPv6 pixel, and a dual stack one to basically see, are you IPv4 capable? Are you IPv6 capable? If you're dual stack, which one do you prefer? That's how they measure it. They do a random sampling. But don't take my word for it. Go read the paper. Right? Again, be informed. Read the data. Look at everything. Make your own decision, because you should be confident in whatever choice you make that it's the right choice and you're confident in the data that you looked at. Same thing for Apnic Labs. Actually, I like their system better. And actually, Google is a major sponsor, by the way. So Google does not view them as a competitor. Apnic Labs actually use syndicated ads. So they use JavaScript, Flash, and HTML5, and they use the syndicated ad system on the internet, and basically they do the same thing, where they try and connect you to a v4, v6, or a dual stack resource. And by doing that, Apnic Labs thinks the US penetration rate is around 30%. So again, Jim, excellent question. 30% penetration or adoption, this is capability. This means this percentage of users is capable of speaking IPv6. But it doesn't necessarily mean that they are, only that they can. But when they say capable, it means from the user's browser all the way through to Google or Apnic, that entire connection end-to-end is IPv6 capable. That's what that means. Okay, and then the third one is Akamai. So Akamai is a content distribution network. So if I'm Apple or Microsoft or somebody and I publish patches or updates and millions of people are downloading it, no one web server can handle that. So I use a CDN. The CDN distributes it out to the entire world, and everybody can download stuff at high speed. So among CDNs, Akamai is the 500-pound gorilla. They are the largest by far, and they serve about 1/3 of the world's traffic. So they're in a pretty good position to judge. Actually, their percentage has been going down. It peaked at 20, and it's actually gone down. So I don't know. Akamai mainly serves the enterprise, and the enterprise has been somewhat cool towards IPv6 outside of Silicon Valley. So, and you can definitely see it there. So a lot of the adoption is more with carriers, content providers, and residential users, and not as much in the enterprise. But you can see, like if you look at the top 10 from each, you know, it's markedly different. But it's not way off. You know, it's in the ballpark. So, but I mean, even as you can see by these numbers, I mean, the traction with IPv6 in the last couple of years is pretty significant, right? So Belgium, you know, depending on who you believe, a third to half their traffic is IPv6, or a third to half of their users are IPv6 capable. So I mean, that's significant. Okay, so when does this get interesting? So when I'm evaluating a technology, I would say that it gets interesting when it hits critical mass. And critical mass, depending on who you ask, is somewhere between 10 and 20%. So in the US, we are definitely there. Now, as soon as you cross the critical mass threshold, does that mean it's interesting to you? It depends. You know, so if I'm a Silicon Valley company, most of the Silicon Valley companies, or a lot of the Silicon Valley companies have already deployed. In fact, like if I look at like Apple or Google or Oracle, Apple's actually IPv6 only. They basically decided that IPv6 is it, and they're totally limited at IPv4. So basically at the internet border, they don't do NAT 6.4, they do NAT 4.6, because they're IPv6 only. Google is basically a similar direction. Oracle, Microsoft, Apple, LinkedIn, all those guys are, you know, fully dual stack, fully deployed, done for years, right? So there are some companies that are already there. What I did here is Google and Apnic Labs have been collecting data for the last 3 or 4 years. So using that data, you can actually do a statistical projection and say, okay, based on the data, where do I think we're going to be? And I can say with a fairly high confidence interval, those numbers should end up being pretty close. I would say plus or minus, you know, 5 to 10%. So I would say in a year, we're going to be at 50% capability. Not usage, capability. So half the users will be able to use it. 2017 will be at a super majority, and then beginning of 2018 will be at 80%. Question?
You really think that growth is going to continue to hold? Because I know we got a handful of really large carriers that serve most of the home users in the United States. And I know, for instance, Comcast was demoing. I think they've actually rolled it out. I'm not a Comcast user currently, but I mean that's a huge quantity of users right there that a lot of them don't even know. It just starts being available.
It just works.
And we have the large tech companies, the enterprises that have the technical savvy staff. But, I mean, I have a history over 20 years plus in IT of dealing with a lot of smaller companies where they're frankly just struggling to get by. I mean, basic firewalling, IPv4, DNS, I mean, still, you know, that's kind of making the leap to IPv6 isn't even at all anywhere close to the wheelhouse where they're going to be anytime soon.
I mean, it's got
in all those places, standing on top, all the business-to-business stuff, things.
Sure.
I see that hitting a wall really soon.
It's a good point, and the truth is, I don't know. You know, will these numbers hold? I think they will, but now once you get here, it's probably going to be a very long tail, right?
Yeah.
Now, I think a lot of enterprises are kind of like a home user, right? If IPv6 is totally easy and it just works, then they might use it. If it doesn't, they won't. But it's pretty much gotten to that point, right? Because Comcast is a good example. If I have Xfinity, it's fully deployed. If my home router supports it, it just works. And that's how it has to be. If it's not like that, people won't use it. Now again, though, this is just capability. I'm not saying that 80% of people are going to use IPv6. I'm only saying that they will have the capability to use it, because those are two very different things. So let me come back to that in 1 second. And then if we look at this data, so here's the current estimated U.S. population, estimated number of internet users. So 30% would be 84 million people that are capable of using it. That's the current estimate. So it's significant. Now, let me throw some cold water on that, right? So I don't want to seem like an evangelist. This is the Amsterdam Internet Exchange. So an internet exchange is essentially a data center where all the major carriers or internet service providers and content providers all come together to peer with each other. It's an exchange point, right? So this is how all the traffic flows back and forth. We have, maybe half a dozen of these in the US, and they're scattered throughout the world, right? This is like the junctions between all the internet service providers and content providers. The Amsterdam Internet Exchange is one of the largest in the world, and Europe doesn't have, on average, it doesn't have quite as high of an adoption as the US, but it's pretty close. And if we look, in terms of volume or actual usage, the amount of IPv6 is about 1.2%. So I mean, it's 1.2% is actually significant, but it's pretty small, right? So in terms of actual traffic, the rate is pretty low, right? And to go back to your question about how many people are going to use it, right? Again, capability and actually using it are two different things. So that's really, it's a very good question, because if somebody has IPv6, when are they actually going to use it? And that's a really hard question to answer. I don't know. I can't think of a way to predict that. I can just predict the capability. Okay, so within the US, here's what it looks like for the major providers. So if I look at the major wireline providers, you know, the top three have a pretty good story. Comcast is fully deployed for residential. So if your router supports it, you have it. AT&T is pretty far down the path. Time Warner Cable is moving along. However, if we get past the top three, Verizon is kind of a question mark. I know they're working on it, but they don't have a very good story to tell. CenturyLink, 0.1%. And if I look at 6, 7, and 8, it's not too much better.
Wow, so they didn't even have any plans on AST.
Who?
Wow.
Well, yeah, the smaller providers, you know, I mean, so, you know, if I put my business hat on, if I am a small wireline ISP, I have less than 1 million subscribers, which in the ISP business makes me pretty small, and I have plenty of addressing, and I have very little growth, you know, maybe I don't have a lot of incentive to do it. Right? Because the incentive is if I have growth, if I have new services, if I'm getting into IoT, if I'm in the M2M space, if I'm in the mobility space, then I have incentive. But if I don't have any of those things, then maybe I don't. So you know, it's that said though, the US is kind of skewed in that if I look at the top 5, I mean that's probably just about 80% of the users. So, I mean, the small ones might be drug along just because if all the big ones do it, they might have no choice. But again, that's kind of hard to predict.
Jim, as a home user, would I have any reason to demand, want, request my ISP to hook me up for 6 and be done with 4? Do I get better performance out of it? Do I get better security?
Can I come back to that in a second? It's a good question. Let me get you in just 1 second, because I have some data. And this is on the wireless side. On the wireless side, actually AT&T and Sprint just started deploying this year. However, the World IPv6 launch website that tracks all the carriers. Basically, if I look at all wireless traffic in the US, over 1/3 of wireless users are already IPv6 capable. And because with your phone, you refresh it every 2 to 3 years, this is going to ramp up really fast. So this is, I would say, as a business or as a person, if you do mobile apps, you absolutely should be all over IPv6. Because in a year or two, this is probably going to be 60 to 80%. Just because you have that constant refresh base. And also the growth here it continues to be really high. Because remember, all those M2M devices are also using cellular connections. So there's tremendous growth and pressure on the address system. So for here, I think there is a good story. And then I threw in Hughes. Hughes is the largest satellite provider. They have over 1 million subscribers, and you know they're doing pretty decent too. Okay, this is probably too much into the weeds, but just to get an idea, if I look at all ISPs globally, so anybody who does transit, so in other words, if I'm trying to get to Yahoo and I'm going through somebody's network, but I'm not reaching Yahoo yet, I'm just traveling through the network, that's called a transit network. This is showing all my transit networks globally and how many of them have deployed IPv6. So if I look, the major ones are pretty far done. And this center here, this is basically kind of the core. All the tier 1s, tier 2s, all the top providers. The ones that haven't deployed tend to be more out at the edge where they're like the smaller ones. So from the internet core, the story is pretty good. Okay, another interesting statistic is content, right? So I have my users I have my ISPs, and then I have my content. So from a content point of view, do I have IPv6 content? So if I look at the top 1,000 sites, about 17% of them have IPv6 deployed. You know, so Google, Facebook, Wikipedia, Yahoo. I'll show a list. There's a lot of major properties that have it. However, as I go down to the smaller providers and I get outside the top 100,000, top million sites, the percentage gets pretty low, down to 6%. So for now, it seems to mostly be the bigger players. And I also thought it was kind of interesting, if we consider IPv6 a site element, like CSS or HTTP 2.0 or strict transport security, that's kind of how it ranks. So, you know, it'll probably be a long time before it gets to 100% if ever, but, you know, even if it gets to half, that'd be significant, because look, half of websites don't even use cookies. So just to kind of give a little bit of context around that. Okay, so I don't want to spend too much time, but I just to give a few examples of companies that have deployed it, right? So a lot of people in Silicon Valley, you know, Facebook, LinkedIn, YouTube, Oracle, almost all the operating system vendors have deployed it. So the only one, actually I was a little surprised, the only one missing is Ubuntu. They do not support IPv6. I was a little surprised by that, but
When you say they don't support it, what do you mean?
so the operating system does, because Linux is supported for a long time, but the company doesn't. If you look at their website, it's not supported. So that surprised me a little, although when you see the cloud slide next, that might explain it a little, because really for Ubuntu Cloud is their focus. Networking vendors have pretty much all done it for a long time. Security is mostly pretty good. Common services, Netflix, Instagram. However, there are a lot, so we saw, right, over 80% of companies haven't deployed it, so there are a lot of major companies that haven't. And I thought it's interesting if you look in the industries. So cloud is a little surprising, right, because that's where there's one of the pressure is felt most acutely in cloud. There is tremendous exponential growth. Getting address space is really hard, and yet the cloud providers are dragging their feet. So that's an interesting one. So I didn't put IBM Software up here, they're number 4. They actually have fully deployed IPv6. But if we look at the top 3, Amazon doesn't have it. You can get it through through ELB. So you can basically have an IPv6 load balancer to translate your IPv4 app, but they don't natively support it. Azure doesn't support it at all. They said they're working on it. And then Google, this is really a surprise since they have it everywhere else. They partially support it, but if I look at the Google Compute Engine, which is their major cloud service, it's IPv4 only. So that one's, I'm a little surprised that in 2016 it's still like that, but it is. Compute, none of them are interested. All IPv4. Storage, same way. And then a lot of the mainstream sites. If I look at all my media sites, New York Times, Huffington Post, newspapers, Reddit, PayPal, Stack Overflow, GitHub, a lot of developer sites, none of them support it. GitHub, I know there's been a lot of pressure on them and nothing. So it's definitely a mixed bag. You know, some companies are doing it, but a lot aren't.
So if I turn off IPv4 support on my laptop, I can't talk to those sites?
Not without translation or proxying. Okay, so this is one question I have spent a lot of time thinking about. So why is there so much reluctance? Why is it so hard to deploy IPv6? And really, in a totally separate industry, I heard a great analogy that I really liked, the interface analogy. So imagine that I told you that the utilities are going to change our power standard, and we're going to have a new voltage standard, and you know, it'll be a little more efficient. You know, there's not really much of a big benefit to you, but for the system as a whole, it's a really good thing. But it means we have to change all the outlets. What do you think? A few months?
We've already had that. That went from 2 to 3.
So yeah. So when you have a commoditized interface like an electric outlet that everybody uses as a standard, and you try and change that, that is really hard, right? Because it's a commodity. And by definition, if something is a commodity, if I change it to something else, it's a commodity. Who cares, right? So I don't want to do it. I don't want to invest in the commodity. And That's really, I think, the biggest problem is IP is a commodity. But with home users and businesses, nobody cares about IP. I mean, maybe this group is an exception, but I talk to developers all the time. You know how many developers are really interested in how HTTP works or how internet routing works? They don't care. Most of the developers I talk to, they say the internet has infinite bandwidth and 0 latency and should do whatever I want. And if it doesn't, fix it. Right? That's the extent of caring. So nobody cares about this problem. So changing the API from IPv4 to IPv6, because at the application layer there is, not across the board, but in most languages there is a difference, that's the resistance, because it's a lot of work, and really, am I getting any great benefit? In the short term, no. Right? So I think that's why there's the resistance, and I can kind of see, right? Because there's 5 million cool things I can do. There's all I can write mobile apps and make all this money, and you want me to deal with IPv6? Go away, right? I'm busy. So the other thing is, it's also very much like the grid. So remember, like 5 or 6 years ago, we had all kinds of grid problems, right? And really, when you plug something into the outlet, do you stop and think about how it works? Or do you worry about, is your local power company healthy? Do they have enough? You don't care. It's a commodity. It should just work, right? And I think that's how we think of the internet. It's not my problem. Somebody else should deal with it. The carrier should fix it. Whatever. I'm busy. Go away. So I think the combination, and plus inertia, we're kind of comfortable with IPv4. I've memorized all my IPv4 addresses. I don't have time to learn anything new. Go away. Unless it's going to make me money. So I think the combination of these three things has kind of created a formidable wall that's hard to climb. And that's where we're stuck. However, even though there aren't a lot of benefits, there are some. And I kind of in the past, I think with IPv6 is a bit of the tragedy of the commons. But again, all of us are here because we're in an industry we like. We want to do cool things and make money. And I don't want to do something unless there's a benefit. So is there any benefit to IPv6 that would make me look at it? And it's not very strong, but there are some. So there's three things. Number one, if you're doing anything with IoT, with the Internet of Things, you definitely this needs to be on your radar. So, for example, since we're in Detroit, let's talk about connected vehicles. Gartner says by 2020, we're going to have 250 million connected vehicles on the road. And Gartner is not an IPv6 fan, but even Gartner will say, and pretty much anyone else in the industry will tell you, that there is no way that is happening with IPv4. It's impossible. You cannot make it work because of the scale. So now, doesn't mean it's going to happen this year, but before 2020, right, everybody agrees that there's got to be a transition to support that kind of scale. So if you're doing anything with IoT where there's billions of things coming online, you have got to start looking at this. Mobility. So Facebook. So going back to your question, Dave, about is there any benefit for a user? Facebook did a study. Now, Facebook, most of their users are mobile from their smartphone or their tablet. And they basically looked, and they saw that, they basically have 10% of users globally connect to them with V6, 23, this is from mid-year, 23 from the US, but they start narrowing that down to just 3G and 4G. With 4G connections, that goes up to 45%, and now it's over half. And all of their growth and all of their focus is on mobile. That's where I think they said they make 80% of their money from mobile. Right? So for Facebook, IPv6 is huge, and they took all of this data that they got from 4 different carriers. They had one of their data scientists analyze 2 sample sets of 155,000, and they conclusively found that there was a 15% better performance with IPv6. Wow. They suspect that's from CGN, but that's not conclusively proved. Now, 15%, it's something, but is that awesome? Is it worth doing something? I don't know. You tell me. Right? You'd have to look at your company and say, is that enough that I care? Maybe, maybe not, but Gibson?
Well, so I suspect that perhaps people who are using IPv6 have newer equipment. So is there any, so when you say the performance...
Yeah, but the newer equipment is using both IPv4 and IPv6, and they're measuring it from the same equipment. And the performance is better with IPv6. So it's not the handset. They don't know conclusively what it is, but it definitely is in the handset, because the same handset is using both V4 and V6.
When you say they suspect it might be because of CGN, does that mean because they're not going through CGN with IPv6?
Yeah, exactly.
Okay.
So,
So it should reduce latency too, then.
Well, there's no NAT at all, is it?
exactly.
So not even
Here's,
the first layer.
here's part of what I suspect is if I do CGN, instead of going straight to the device, I'm going over here.
Yeah.
Right, so if over here happens to be out of the way, or this guy happens to be loaded, even a little bit,
So it's another
That-
hop with some translation.
that's right.
Yeah.
So, now, some people have done studies and say that they don't see that much, so I don't know, it's a possibility, yes.
What is the, or is there any increased overhead due to the longer addresses in each packet?
That's true, there is, so the header size is double. It goes from 20 to 40 bytes. However, for practical purposes, it's really not significant. Because there's a lot of things, anybody doing virtualization, they put all kinds of headers on that are far bigger than that, and they still don't notice a significant difference. So I would say it's, really it's not a significant amount.
Is there difficulty routing between the two?
That is a good question, but let me come back to that, because I have a slide on that. Okay, last question, and then I love the questions, but I gotta move us forward, I'm gonna run out of time, yes.
You mentioned this really early on, and if you're gonna get back to it later, I can wait, but my big reluctance is tying my internal address space to the provider assigned network address.
Okay, that's an excellent question, and I'm not gonna directly answer it, but let me go through this, and then I'd be happy to talk to you more if, at the end.
Okay.
Okay, so, one other thing I wanna talk about is mobile. So, the big fear back in 2011, 2012 is we knew we were gonna run out of IPv4 addresses, but we didn't, back in 2011, we didn't really think that CGN was gonna take off, right? So, a lot of people thought there's gonna be IPv6 only users, there's not gonna be any way to talk to IPv4, and you have to support IPv6 or you're gonna be SOL. That didn't happen. So there are actually IPv6 only users. So in the US, T-Mobile USA, which is the third biggest wireless carrier, they do IPv6 only for the vast majority of their devices. However, they have a translation service to get you to IPv4. So that was the part that wasn't predicted. So if we look at how this works, I have a smartphone that gets an IPv6 address, and then basically, if I'm going to Google, which natively supports IPv6, then I just go straight to the site, and I'm good. However, most of the internet is still only IPv4. So if it's an IPv4 address, basically when I do a DNS query, I'm going to use a special server that has what's called a DNS 6.4 service. And that DNS server is going to go, uh-oh, there's no IPv6 resource record. So it's going to synthesize or create one. It'll basically take the IPv4 address, turn it into hex, add it on to an IPv6 prefix, and then send that back as the answer. That prefix will route the traffic to a NAT 6.4 gateway. The NAT 6.4 gateway then translates it to IPv4, uses the embedded address to say that's where you're going, and then sends it on its way. However, to do that, especially the DNS 6.4 part, it is a significant amount of time. I mean, we're only talking, tens or hundreds of milliseconds, but if you're over 150 milliseconds, your users are noticing. So if you're a big site, it's probably not a problem because you'll be cached, but if you're a smaller site, that's a little bit of an issue. So if you don't support IPv6 on the mobile front, then you have 60 to 70 million users that are not getting optimal performance. The other thing is, not everything works through NAT 6.4. Most stuff does, 80 to 90%, but T-Mobile will tell you some stuff doesn't work. So if you're like a major app like Skype that doesn't use NAT 6.4, then they actually created something called 464 XLAN. So we basically fake that we pretend that we have IPv4 on the handset, even though we don't. Then we basically tag certain applications like Skype. Says, okay, if Skype tries to send traffic, pretend like we have an IPv4 address, then translate that traffic to IPv6, send it to the NAT64 gateway, and then that spits it back out as IPv4. That's called 464 excellent. And so I'm kind of rushing through this, but the point is, that's only if you're a major app like Skype. If you're not a major app, and you don't work through NAT64, guess what happens when somebody tries to go to your service through T-Mobile?
No good.
It doesn't work. And you know what? Who is the user going to blame? Are they going to call up T-Mobile and say, why can't I get to this site?
Probably.
No, they are not. They're going to tell you that your site sucks and they're going to go somewhere else, right? Because people, I can tell you from working through this issue, an end user always blames the end site. They don't understand the internet, they don't want to understand it. You know, basically, like if I talk to my wife, either Facebook's working or it's not. Honey, Facebook's broken, fix it, right? You know, my wife is a sharp person, but she doesn't care about networking details. I want to get to Facebook, make it work. You know, I don't care about the details. The end user, that's how end users are, right? So this is one thing. If you're in the mobile space, this is significant, right? Because T-Mobile has almost 70 million subscribers. So this is definitely something you should factor in. You should at least test your app and make sure it works through NAT64. Okay. I probably spent too long on that part. So coming back to your question is, if I am an enterprise or an organization, if you're home, it's a lot simpler. What makes sense to consider with IPv6? So if it were my company and I had, you know, a sizable company that was, you know, like $1 billion or more, would I deploy IPv6 internally right now? Probably not, right? Because if I'm talking about, if I have, you know, hundreds or thousands of sites and tens or hundreds of thousands of nodes, can you imagine how much work it would be for me to put IPv6 on all those? That's a lot of work, right? For you know, hazy benefit, if any, I think that's a tough case. However, what I would consider is at least put it on the edge, right? Because we know it's coming. We're past critical mass. We've shown sustained growth, sustained exponential growth for 4 years now. So this is pretty serious. So I need to start ramping up my people so at least they get their toes wet and start getting around it. So what I would do is, at my edge, the first thing I would do is I'd talk to my ISP and I would get them to dual stack me. So I have V4 and V6. So any major ISP will have this. If your ISP, if you have a business grade ISP that cannot give you IPv6, honestly, when your contract is up, you should go somewhere else. I mean, that's, at this point, that's pretty sad. And I haven't run into that for a while. Tier 1s, Tier 2s, I think all, even the small ones that don't offer for residential, as far as I know, they all offer it for businesses. So I'd be surprised if you still ran into it, but if you did, I mean, there's so many alternatives out of this shop. So on your border router, that's where I would turn it on first. When you turn it on, it's really not that big of a deal. And the reason that is, just to skip ahead a little, is IPv4 and IPv6, there's kind of a saying in the network world called ships in the night. So IPv4 and IPv6, they're basically like two ships passing each other in the night. So if I'm a passenger on one of these ships, and I'm passing this ship by in the middle of the night, do I interact with the passengers on the other ship? No, I'm basically completely oblivious to them, right? So IPv4 and IPv6, they are completely in parallel. They are orthogonal. They do not interact at all. So this is one thing that's a little confusing. If I tell you that, you know, IPX or SNA and IP don't interact, that's kind of easy, right? Because they have different names. But IPv4, IP, I mean, aren't they both IP? No, they are totally dissimilar. So I mean, there is a relationship, but on the wire, they are totally orthogonal to each other. There is no interaction at all. So I know a lot of people have a hard time with that. So there are some consequences, like, for example, one thing that you have to be careful is if you take your internet router and it's running SNMP, right? And you probably lock it down so only your SNMP management station can access it. Well, if you enable IPv6, by default, it's wide open to the entire internet, which is probably not what you want, right? Because that IPv4 access control has no impact on IPv6. So all the security controls you have in IPv4, you have to figure out how to do that in IPv6. It's going to be different. It will not be the same. So that's one thing you have to be careful on. You know, however, I mean, it's pretty straightforward. I mean, it's just, you know, looking in the manual, figuring out how I do it, and away you go. So what I would do is I'd start out with the border routers. generally it's not a big deal to deploy them there, and then I can just incrementally bring it in. On any modern equipment, like any modern Cisco device, they've been supporting IPv6 for like 10 years, and unless you're way behind in code or have really old devices, for your perimeter devices, for all of this really shouldn't be a big deal. And you gradually bring it in. You know, first the border routers, then the firewalls. To answer your question, I would not bring it into my corporate network. I just, you know, if you're a small company and you like it or something, or maybe you're a high-tech company and you have lots of brilliant people that like doing things for fun, but for a typical company, I probably wouldn't bring it here. I would stop on the edge. And I would basically look at incrementally enabling it on my DMZ. So for example, to support VPN is an easy one. All I have to do is I put IPv6 just on the internet-facing interface. Basically, an IPv6 only user can VPN into the company, and I can still assign them an IPv4 address. So everything is exactly the same as it is today. The only difference is the initial connection or the outer tunnel is IPv6. If I have a partner in Singapore that can't get a public IPv4 address, same thing. I can build my site-to-site connection using IPv6, but all my internal traffic that I and my users actually see can still be IPv4. So IPv6 can actually be really helpful in a lot of cases, and this is not hard at all. I mean, there are a few tricks with interoperability, but I mean, it's straightforward infrastructure stuff. Anybody who's dealt with infrastructure would know exactly how to address any of these problems. Same thing, DNS, very easy. Load balancer is so easy to do, you're going to be surprised. If I want to support IPv6, so I take my web server, I basically have my load balancer have an IPv6 VIP, my application stays IPv4, people talk to my load balancer over IPv6 and it translates to IPv4, very easy to set up. Now my server speaks IPv6, but I didn't have to change anything on the back end. Now you still have to do some testing, you know, you might find some components don't like it, but for the most part it works pretty well and requires minor changes if any. It's the same thing, email, we'll talk, he's not quite ready. And then for IPv6 only internet sites, there are some, but only really because they choose to be. But again, you don't have to let your users have direct access, you can set up a proxy. There's lots of good open source ones. So if there happens to be some kind of IPv6 only internet service, users can get to it through a proxy, right? So that's where I would focus on, and when I have done work with companies, this is what we've done, right? Focus on the edge, reasonable minimum, incremental approach. And when do I do this? You know, maybe in a year or two, right? Figure out how long it would take me. And really, I have to define for my company, when does it get interesting? When is there enough of a benefit to go further?
You'd still be beholden to the provider address though, right, in that scenario? Which means that if you cancel your contract, switch providers, you're gonna have to figure out how to do everything, right?
If you're multi-homed, you automatically qualify to get addresses directly from ARIN.
But if you're in that uncomfortable small business spot where you're not big enough to be
that's
multi-homed,
true.
That's a huge
That's true, but
liability
you can,
cost that you're holding.
but as much as the IPv6 crowd would hate to admit it, you can still do NAT.
Okay.
So,
I've read some conflicting articles, I've never tested it, but.
yeah, not everything supports it, but it's more and more common. So it's still an option. So, but again, if you limit it to a small area, a few pieces of equipment, it's not a major investment. It's not that. And if you have to change IPv6, remember it has no impact on IPv4, right? So the impact is relatively small. Okay, I talked about this, about watching it with security devices. Okay, and if you host content or downloads or something like that, there is an easy button with CDNs. So Akamai I already mentioned, Limelight's another one. Cloudflare is kind of like the darling, everybody loves them. I think they're really cheap because I even know a lot of blog sites that use Cloudflare. So there's lots of options. If you want to do it and you want an easy button so you don't have to deal with anything, you can just use one of these guys and basically they act as a reverse proxy for you. And actually, in the case of Cloudflare, I know they do all kinds of advanced caching, and you might even get better performance. So, you know, if you're interested but don't want to do any work yourself, that's worth looking into. Okay, so when I talked to Jim, I was thinking I was going to go through a lot of these, but really a lot of these, like, if I was going to talk about Quagga, that'd probably be a whole talk by itself, and I don't, you know, this isn't really exactly a hardcore network crowd, so I think a lot of you guys might be bored with that. But I listed them. So especially in the routing space, I've done some research there. If you're going to use one, I'd use Quagga. So if anybody deals with open source networking, probably the biggest name right now is Cumulus. You may or may not have heard of them. But Cumulus, they basically use all open source for their networking stuff, and they contribute back, and they use Quagga. So if you're going to use an open source routing daemon, and that supports BGP, OSPF, RIP, pretty much everything, that's the one to use. Now, if you're an enterprise and you're on Quagga, I think you're nuts. If you're an I mean, I hate to say it, but for the high end, you got to get a commercial solution. You should stick with Cisco or Juniper or somebody on that level. But for the mid space and below, I think Quagga is pretty solid. And then I mentioned some other ones. Load balancing. I'm actually going to do a small demo with HA proxy. I don't do as much with this stuff, but my kind of straw poll sense is that HA proxy is the most popular. Nginx is also really popular, and so is LVS. But just some ones, you can look into if you're curious. And then for proxy, Squid is the most popular. Not necessarily the best performing, but the most popular. I put in some other alternatives, and then I just threw some other stuff in. So if you want to stick with open source, there are a lot of good options for this that all support IPv6. All right, so what I wanted to show is I can't really see, but
Big red line.
Yeah.
oh,
Diagonal.
that's better. Now I have to try and do both at the same time. So. Okay, so, forgive me, I'm not a Docker whiz. So I basically have a container in Docker, and it's basically using Docker 1 as the network, and as you can see, it only has IPv4, right? So this is a typical company, only has an IPv4 address. And what I can do is, so this might be gibberish if you never looked at HA proxy, but I mean it's a typical load balancing application. So in a load balancing application, I'm going to say what's my VIP or my virtual address that I listen on. So the VIP is what does the end user actually connect to that the load balancer services, and then the load balancer proxies that connection and then turns around and picks the real server that actually serves the data. So this is what it looks like if I do IPv4 bind space *:80, so any address on the HTTP port or service it listens to. All I have to do is change it to the IPv6 notation, which supports both v4 and v6. That's literally all I changed. Very simple change. As long as one of the interfaces on my box has both IPv4 and IPv6, now the load balancer is dual stacked, and just doing that, it'll now translate any incoming IPv6 request to IPv4. That's it. It's that easy. Now, I don't want to say this is totally painless. When I work with people, if you have a lot of stuff with Flash or Silverlight or complex Java stuff, you might have to do some tweaks. But actually, it's usually, I would say, 80 to 90% of stuff just works, and then the rest of the stuff needs some little tweaks. So it's relatively easy. And then if I go back to Okay, so this is a super basic website, but enough to get the idea. So there's actually a kind of a cool plugin for Chrome and Firefox. It's called IPv4 for Chrome and IPv6 for Firefox, and that's this guy up here. And what this does is, that basically shows me what am I connecting to. So on a typical website, you might have 30 things, and for each element, it's gonna show you what's the address, v4 or v6, so you can actually see. And then what I can do is I can go back up here.
Yep.
It's kind of hard to see from this side angle. Oh, I forgot. I forgot my company helpfully blocks all IPv6 traffic, so I have to disable my firewall. Save it.
We're not seeing how you do that.
Yeah, I can't because I have a split screen. This is one thing I didn't think of.
We can do without it. Something that's good.
Alright, well, I need to try one more thing and then I'm gonna give up.
Good time to grab a cookie.
Always a good time to grab a cookie.
Alright, well,
Is HA proxy running on that server?
it is. Alright, well, I apologize, I did not try my demo when I got here, so. But, I'm a little bummed that that didn't work, but I will say that, you know, typically, I'm running that in a VM, so it makes it a little trickier, but typically it's pretty straightforward. So if I have any major load balancer, F5, I'm drawing a blank now, but Citrus's load balancer, HA proxy, anything like that, it's basically very straightforward. My VIP, I set it up for V4 and V6. My server configuration on the back end is the same, and really that's it. If I have routing and everything set up correctly, it just works. So it's very straightforward, so especially for publishing your apps, it's not a lot of effort because unless your load balancer is pretty ancient, most applications you're going to use a load balancer to front end. So it's literally just going to that load balancer and configuring it to support IPv6, and that's it. So it's not a lot of work. Okay, email is not quite there yet. Basically, if I look at email, this is just for the top 500 sites. I don't know of any great global statistic for email. It's not as well tracked as the web. Cisco says 1 to 2% of internet email is IPv6, and that probably sounds about right. The challenge with email is, and depending on who I ask, I get a different story, but from what I gather, a large component of blocking spam is based on address reputation. And for IPv4, where I only have 4 billion addresses, that's a pretty easy problem. However, for IPv6, just in one network, I have 18 quadrillion addresses. And the number of addresses is like 300 and something undecillion. It's basically meaningless. The number of addresses in IPv6 is too big to comprehend. It's insanely big. And so the challenge is, if I try and have an address-based reputation system, it would be, the database would be so big that you couldn't download it, you couldn't distribute it, right? So it doesn't work, right? So the current model does not work with IPv6. And I think we're still kind of in the research phases. You know, I mean, I can still do all my domain stuff, I can still do all my authentication stuff. I still have some options, but my address space stuff is now pretty much worthless. You know, and there's some proposals, what if I just use a network or this or that, but it's still early days. So because of that, it might be worth playing around and making sure your on-premise or cloud solution supports it. Most of them do. But would I actually turn on IPv6 email and leave it on? Probably not. And then just kind of doing a little research here, if I look at the top email providers in the US are basically Google, Yahoo, Hotmail, AOL, and Comcast, believe it or not, are the top 5. And I believe only Google and Comcast support IPv6 email and only inbound. So I mean, that gives you an idea, right? If most of the major providers don't do it, you know, I think email is not quite ready for prime time yet. Okay, and one other thing I wanted to show too is another common question I get is, especially because a lot of people are unclear that IPv4 and IPv6 are totally different protocols, is, I mean, can I just NAT it? Can I just put a NAT gateway at the edge and translate all my IPv4 users to IPv6? You know, why can't I do that? So I wanted to take a minute to talk about the IETF is who does all the standards for the internet and for communications. And they came up with an RFC 6144 that basically talks about this problem. If I have an IPv4 network or an internet and an IPv6 network or internet, and I want them to be able to talk to each other, I'm going to stick a translation device in the middle, and I have 8 use cases. And I want to look at each one of those use cases to see what is possible. So this shows. So if I have, I'm not going to read through all of them, but you can see and you can get the deck. So that there's 2 variations. There's stateful and stateless. So in the IPv4 world, we only have stateful. Stateful means that when I do NAT, the device doing the NAT actually has to keep a record in memory. So when the connection comes back through the router, it looks up its connection table, it has to find a match, and then it unnats it. If I reboot that router or it crashes or something like that, then my connection's hosed, right? It's gonna fail. That's a stateful connection. So that's a bit of a problem too with CGN, because in TCP/IP, the more state that we push into the network, the more fragile the network is. So if I have a stateless network, I can reboot stuff, I can take it down, I can change paths, and you won't even notice. It's instant, which it's great. And that's how you want a network. You want a network so I can take half my network down to service it and nobody notices. However, if I have stateful, then I can't do that. Or if I do that, then I have to have complex high availability schemes, because if I do something that disrupts the machine holding the state, then it kills and disrupts all that traffic. So that's kind of a challenge with NAT. Now, stateless is where we use, one second, Gibson, I'll get you, stateless is where I have an algorithmic mapping, right? Where I use certain special addresses, and when it sees that address, it recognizes it and just knows what to do with no state. So the cool thing about stateless NAT is if we do that, and we reboot that router, and then the connection comes back through, it still works, because no state is necessary. However, it's not as good as it sounds, because when you look at the addressing restrictions, it's generally not very desirable, but it's an option. So this kind of goes through all the options, but what I want to point out is, if I look at use case 7 and 8, can I go from the IPv6 internet to the IPv4 internet or vice versa? The answer is no. It is not possible, and that's because if I look at IPv6, it's so many orders of magnitude bigger than IPv4 that it's just not possible to scale a solution out that much. So I can't do it. So can I do subsets? Sure. You know, can I take one network and get it to another, or I can do limited restrictions? Yeah, I definitely have some options, but this is not a silver bullet. And there was another one too that was kind of popular. Can I take one IPv4 network, just one, and translate it to the IPv6 internet? And there was a predecessor, this is using NAT64. There was a predecessor to this called NATPT, and NATPT supported that. But NATPT was basically jettisoned because it was too slow. The performance was awful. At any significant scale, the performance doesn't cut it. And so basically the IETF said, doesn't cut it, tried it for years, can't get acceptable performance, so they scrapped it, and they came out with a restricted subset, which is a NAT64. And so if I want decent performance, I cannot support that use case. So again, I definitely have some options, but there's no silver bullet or magic solution where I can just put in this gateway and everything's gonna work. Even a proxy's a great option, but only where the proxy understands the protocol, right? So for HTTP, that works fairly well. But, if I have, any kind of like SIP or video or real-time chat or XMPP or anything like that, proxies don't support protocols like that. So it only works for simple traffic. So there's no easy way to just say I'm gonna have this magic gateway that's gonna prevent me from having to convert to IPv6. And because of the scale, it's just not gonna happen. Okay, and then, I want to get a little bit into the weeds on this part. So, another question I get is, why is this such a pain? When people invented the internet, why couldn't they make it like the phone number system, right? So if I look at the phone number system, if I want to like add an area code or change the number of digits, I can do it. Why can't I do that with IP? Why is this such a pain? And actually that would again be a whole other talk to explain why that's the case, but that's how it was designed. And the problem is, and anybody who's getting into the SDN space, I've actually seen some really interesting talks about this, the problem is with the abstraction. So, when I look at networking, if I have a proper abstraction, when the user talks to the network, they would see like a top level name and that would be opaque. They cannot see under the name. If that was how IP was set up, that you had to use DNS and the address was hidden from you. So for example, with the file system, right? Anybody who writes code, when you write something in Python or Ruby to open a file, do you worry about what kind of file system it is? No. Does it matter if it's Linux or Windows or OS 10 or Unix or real-time operating system? It's all the same because that's hidden, right? I get a file descriptor and the details are abstracted away. And unless I write file systems, I don't care. I write to the file descriptor and it just works. And that's really what we need for IP, but unfortunately we don't have it. With IP, we don't have a good abstraction. Instead, I have a name, but the name passes back the address. So the address is not abstracted away. So that means the application sees and deals with the address. So that means if we change the address at all, we have to change the application, usually. There are some exceptions like Java. If you use the Java socket API, it actually abstracts it away. And if you don't do any cute tricks, you just use the standard API, then it just works. But Java's an exception. Most languages, you still deal with the address, and that's the problem. That's a big part of why it's so painful. And I wanted to, so I am definitely not an expert coder. I'm a dabbler, but at least I'm hoping this will give you an idea. This is in Python. So this is kind of my classic socket code, right? So I basically, I import my socket library, and then typically I'm going to do a get host by name. So my user is going to pass me a fully qualified domain name like www.yahoo.com. I pass that to get host by name, and that returns me an IPv4 address. Now that whole call is IPv4 only. It will never work with IPv6, right? Then I basically connect with my socket. I use AF-INET, which is IPv4 only, and I connect. And there's still a lot of code like that. And unfortunately, because the socket API exposes all the low-level details, I mean, it's a mixed blessing, but in the case of IPv6, it's mostly bad. That means that potentially I have to go back and recode. That's why something like a load balancer is so appealing. Or using a CDN is so appealing, because then I don't have to touch my apps, usually. Now, if I want to make that dual stack, I don't have to change a lot, but I have to change a little. So the first thing is, instead of using get host by name, I use get address info. And it's cool, this is pretty universal. Windows, OS 10, Linux, I mean, I think across the board it's pretty much the same. I mean, it does vary a little bit by language, but this is pretty close. Python is very close to C, which is where this all came from, in terms of the socket API. So, now there is a major difference though. With get host by name, when I do that lookup to resolve the name to an IP, I get one IP back. Okay, but we have a problem. When I have IPv4 and IPv6, and I do a DNS lookup on Yahoo, I'm going to get back IPv4 and IPv6 addresses. So which one do I use first? IPv4 or IPv6? How do I sort those addresses? So the answer is There's an RFC called, I believe, 6724, something like that. It basically talks about address selection, right? So I get back a list of addresses. My operating system has what's called a prefix policy table, and I can change that, where it sorts the addresses. By default, in all modern operating systems, and this just changed with OS 10.11, it's finally the same there too, it's gonna sort them so IPv6 is first, unless I change it. But that means that this get address info is gonna return me a list or an array, not just a single address, which means I have to change my code. So notice here, I'm not just doing one connect, I'm doing a for loop, and I'm iterating. So in Python, I don't have to have a count, I can just iterate through a list and it just knows how long it is, right? So I'm iterating through all the elements in that list and trying each one. So this is also a change in your code. So it's not super hard, but it is a change, right? And you kind of got to think through, what if it doesn't work? How am I going to react? Okay, so this goes through. I kind of put in a little hack that said AF equals 2, that's IPv4. So I kind of just wanted to do IPv6, so I said, okay, IPv4, skip it. But anyway, so basically, standard with any language, I do my try except. So I try and connect, catch the error if it fails. And I basically keep going until I get a connection or until I've iterated through all the addresses. So, and then the other thing is, in my socket connection, instead of using AF inet, I use AF unspecified. So it can be v4 or v6. So that's really it, those three things. I have to change how I look up, I have to iterate through a list, and I have to use AF unspec, right? Or if I'm lucky, it'll be like Java and it's all abstracted away. So it's not a huge change, but it is a change. So hopefully, it's a super basic example, but hopefully it helps
Isn't
with
that
the idea.
time consuming for the program to go checking all these different IP addresses?
If the first one works, then it's really no different than IPv4. But you're right. I mean, if like 2 or 3 of them fail, it can be very time consuming. But that's OS dependent. So usually, usually if I were writing a client, what I would do is I would probably set a timer, right? So when I'm at my socket call, I can say like, okay, I'm going to try a connection, and I'm going to wait like 300 milliseconds. And if you don't come back in 300 milliseconds, I'm going to throw it away and try the next one. Right? Because some operating systems might take minutes to time out, and your user's never going to wait for minutes. So usually when you do the socket, you basically set a timeout that says I'm only going to wait this long. But again, in IPv4, it's the same thing. This get host by name, it only returns one address, but it's just picking a random address. So if Yahoo sends you back like 5 IPv4 addresses, it just picks one and give it to you. But it might fail. So that part doesn't really change. However, it is a good question in the sense that if I look at reliability, the average failure for IPv4 is like, I think it's like 0.8% or 0.08%. I forget, but it was really small, like a fraction of a percent. But the failure rate for IPv6, and a lot of this is because of tunnels, not true native IPv6, is more like 1.8%. So it is higher. So I would say in your code, and there's something called happy eyeballs, where if you're connecting to v6, you would actually set like a 200 or 300 millisecond timeout, and if it doesnn't come back, just assume it fails and iterate to the next address. But really, I would argue that that's good general practice, because if you have multiple addresses, you should try and connect to each one, and I wouldn't wait more than 300 milliseconds tops, unless it's a satellite connection.
The time is now 8:30 and the library will be closing in 30 minutes at 9 o'clock. Please be advised that the internet will shut down 10 minutes before closing. Thank you.
All right, so I'm not going to go through all this, but this is from Apple. So Apple's interesting, they're a bit of a trailblazer. So like I said, they've already fully deployed IPv6, and Apple basically said last year with iOS 9, which is already out, if your app does not work in an IPv6 only network, you will not accept it. So they're basically forcing people to test their apps, and your app has to work through NAT 6.4. And what they found is, now another thing, I hear some people saying that Apple should support 464 XLATE because Apple said we're not going to support it. And I've heard a lot of people squawk that, oh, they're killing us. But actually, the way Apple solved it is you only need 464 XLATE for an IPv4 only application. But if Apple can say all apps have to support NAT 6.4, you don't need 464 XLATE, right? So keep that in mind too. I like Apple solutions better. They have some gumption to do it. This is basically showing common IPv4 only calls, right? So if you use Swift or Objective-C, right, you have to avoid those calls. Those are IPv4 only calls. And what was also interesting is they found that really the big one is get host by name. But they also found that a lot of people check to see if they can reach, if there's a default route where they can reach an IPv4 address. And if that check fails, this is called a pre-flight check. Basically, if it can't connect to an IPv4 default route or a certain IPv4 address, it just assumes that you're not connected to the internet. And then the app fails. So Apple was saying, no, that is bad code. The way you should do it is, just how I described, is basically you should do a connection, you should set a socket timeout for 200 to 300 milliseconds, and if it doesn't connect, then react appropriately. But you shouldn't try and do a pre-flight check. So I thought it was kind of interesting that they scrubbed a lot of code, and these are the general best practices they came back with. So I'll kind of leave that in there as a reference material. And that's it. So I rushed you a little, but hopefully, I mean, you can see there's a lot of details, but I guess what I'm hoping is, I'm hoping that kind of helps give you an idea of where things are at, and maybe enough information so you can kind of think about, is this interesting to me yet? Or maybe when does it get interesting? So any questions with that? Gibson?
So,
I'm sorry, you asked and I never got back to you.
It looks like IPv6, you have to go through your ISP to purchase it, or do through some kind of elaborate justification.
No. Typically, it's not a cost. Basically, they're flipping a switch. So you call up your ISP.
Okay, so I'm saying you have to go to the ISP and purchase your IPv6, right?
No.
Or you have to go. Okay,
No,
so maybe I
so-
should start over. You have the option of going to an ISP to get an IPv6.
Are you talking about the service or the address?
So I'm talking about getting a service that provides you with the address. So
Okay,
you
well,
have.
let's separate them.
Okay.
So let's put the address aside. So just the service, you would call the ISP and say, turn on the switch. And
Okay,
that's
so
it.
what I'm saying is that's your option, or you could go to the, was it CERN or whatever?
Okay, for the address,
Yes.
you can either get it from your ISP,
Yeah.
or you can go to ARIN and you can apply for your own independent block. That's
Okay.
optional.
All right, so I understand that to apply for that, you have to go through justification. You have to be like a business, you have to be doing an experiment, that type of thing. They're not
That's
just-
true, but ARIN, if you're a small business, it might be a little tricky, but if you're a sizable business, ARIN doesn't make it that hard.
Okay, so for me as an individual, I want to use IPv6.
You'd have to get it from your ISP.
Okay, so now I have a problem. I have an ISP that I can use an IPv6 to provide a service. I come to this library, that ISP is not what I'm using to connect.
Yeah, so if you're in an IPv4 only location, you'd have to VPN to somewhere that could give you an IPv6 address. So for example, what is it, GoGoNet, or there are certain services where if you have an IPv4 only connection, you can actually VPN to an IPv6 POP, and then just like a VPN, they'll give you an IPv6 address. So if you're on an IPv4 only connection, you would have to set up a tunnel or a VPN that would give you IPv6 connectivity.
Okay, so in the case of having like a Internet of Things, you have a device that you want to connect up, and that device moves from one place to another, connects up to a different type of network based on where it is. The current IPv6 going to an ISP isn't going to really provide the service that you need. You'd have to set up a contract with several different ISPs for each of the different locations that you're going to connect to.
I mean, well, so I'm not an IoT expert, but from what I've done, my research suggests that if I'm doing IoT, typically what I do is if like I have some kind of a field sensor, I would contract with one of the major carriers, like AT&T or Verizon or Sprint or T-Mobile, and say, okay, here's my product. I'm just like Apple's phone. I'm going to embed my chip. And I want, X bandwidth rate up to this much data, and I'm going to bake it into the product price, and kind of like with the Kindle, right? If I buy a Kindle, the connectivity's baked in. A lot of the IoT companies that I've read, that's how they're doing it. The service is just baked into the product. So, but it could be a problem. It just depends on how you set it up. I mean, if it has to roam between different networks, then you're absolutely right. That would be a major problem. So it depends.
Yeah, well, I'm just curious if anybody's given thought to how, Internet of Things provided out as, consumable, from consumers would be able to connect to all the different ISPs and things. I mean, so we're used to a cell phone, right? The cell phone always connects to the same ISP, right? So you're basically locking into an ISP on internet, devices that.
That's not
Yeah,
entirely
that's-
true.
no.
So within your native service area, that's true. But if you go out of your native service area, then you roam and you're going through a different provider. And it works pretty fluidly even for IPv6 right now. It's like one of the guys at one of the IETF conventions in, I think in Singapore, he showed that he had, T-Mobile USA service, he had an IPv6 address, and he roamed in Singapore and it still worked fine using IPv6.
With a different provider?
Yeah, because T-Mobile USA doesn't exist in Singapore. So he was roaming through a Singapore provider. So, I mean, I'm not saying it's gonna work everywhere, but it's definitely possible. But you're right, that is absolutely a complex scenario and you have to carefully think through it. Any other questions?
Thank you, Jim.
Great,
Thank you.